Welcome back. So we are discussing two sample non-parametric testing problems, and in this module, that means I am referring towards module 3, and in this module we have already started two sample location problem, and the last class we have discussed Mann-Whitney U-test, which is going to deliver as a location problem. Okay, so this lecture discusses finer details of Mann-Whitney U-test when there are tie case in your data. So let's start the journey. Mann-Whitney U-test statistics under tied cases. In the construction of Mann-Whitney U-test, probably you remember that is we have defined U in terms of Dij, and Dij was the indicator function, remember it? So, but what we have defined that Dij is equal to 1 if Yj less than Xi, and Dij is equal to 0 if Y greater than Xi, Yj I means greater than Xi. But probably you noticed that we haven't mentioned that what would be the situation when Yj and Xi means the jth component of Y observation and the ith component of X observations are equal. So that's the point of the tie case, right? So here we will modify the definition of Dij in case of the equality. So let's have a look. In the construction of Mann-Whitney U, Dij is not defined for Xi is equal to Yj. This expression does not allow for the possibility of ties across the samples. If tie occur within one or within both samples, there will be no problem, means you will always have a unique value of U. However, if one or more X is tied with one or more Y, the formula of U has to be changed a little, right? Now, what would be that? Ut double summation Dij as it was, but for equality cases, you can see that for equality cases, we are assigning the value of Dij as 0.5, okay? So now and onwards, in case your data comprises of ties, then for each equality, you have to assign 0.5, right? On this note, you have to redefine the probability of X greater than Y as P plus and P minus when probability X less than Y. So earlier it was just a probability, means P, that was probability X greater than Y earlier, if you can remember it correctly. But now we are splitting the probability in two parts. One is P plus and another is P minus. That means there is a probability for X is equal to Y. Now expectation of Ut quite obviously would turn as Mn into P plus minus P minus value multiplied by the probabilities. Now Mn means how many observations? Just have a quick recapitulation that you have M X observation, you have N Y observation. So total pairing can be possible for Mn pair. So that's why Mn and P plus minus P minus, because P minus is coming from the negative part of that probability. So under null hypothesis, probability X greater than Y, and that is equal to probability X less than Y, then expectation of Ut turns to be 0. Recall the example 2 from the last lecture. Now let's change one observation, and probably you remember in our last lecture we have discussed that the example of the bush, new hybrid bush and the traditional bush, and we have considered the girth of the hybrid variety as well as the current variety. Now here you will see that there is 36.6. It was earlier, it was the 36.6 it was the value. Now, if we change it 36.7, why we are changing it? Because in the second sample, you will have 36.7. So, 36.7 is here in the current variety as well as 36.7 also here in the hybrid variety. So, basically these occurs a tie, correct? So, now you will see 36.7 occurs twice, once in X and once in Y. Now, you have to redefine Dij as the tie has been occurred. So, Dij is equal to 1.50 Xi less than Yj. You can redefine Dij as 1 if Yj less than Xi. There is nothing wrong in it. Clear? I mean, it depends on you. You can assign 1 for Xi less than Yj, and or you can assign Dij 1 for Xi greater than Yj. So, I already told you in our earlier discussion, as per your definition of Dij, U will be defined. U means the Mann-Whitney U test will be defined. It may be Ux or it may be Uy, right? Now, form the combined sample. In the combined sample, you can see that 21.3, I have just arranged all the observation in increasing order. So, you will see that increasing order here, and as per the observation coming from X population or Y population, we have named it X1, X2. So, that means X1 is less than X2, X2 is less than X3, less than Y1, like this. So, basically this is my arrangement of the combined sample. Now, you know how to calculate out U, okay. So, you know how many times Y precedes X. So, that's you have to count. So, similarly, we are counting that how many times, as we have defined Dij by Xi less than Yj. So, we will see how many Y's are bigger than X, how many times Y supersede X. Clear? So, let us stick to the first Y, that means Y1. Y1 is bigger than X1, X2 and X3. So, the assignment or the score responsible for Y1 is 3. Clear? This 3. Now, the next one, how many times Y2 is bigger than X1, X2, X3? Although I am saying how many times, but you can just by looking at this sequence, you can find out that Y2 is bigger than X1. So, the score is 1, X2, so the score is another 1, so 1 plus 1, 2, and X3 another 1, so 1 plus 1 plus 1, that is 3. So, similarly, you can calculate out the score valid for Y3, the score valid for Y4 and the score valid for Y5, but pause a little, Y5 is equal to X5. So, here you will see 4.5. Just have a check of Y5. Y5 is bigger than X1, so 1. Y5 is bigger than X2, so another 1. Y5 is bigger than X3, another 1, 3. Y5 is bigger than X4, 4. And Y5 is equal to X5, that means 0.5. So, 4 plus 0.5 comes as 4.5. The entire calculation I have already shown by the side, right. Similarly, calculate the score for Y6, it turns to be 5 and the total score for U is 21.5. Also, on the other hand, you can calculate U prime. Now, what will be the U prime? Just redefine Dij. We have taken Dij as Xi less than Yj. You know, you just change it Dij prime, that will be Yj less than xi, just the opposite side. In my last lecture, I told you that is these are just complementary to each other. So from there you will find out u prime as 8.5, and you know if it is a two-sided test, remember it is a two-sided alternative, you can see here. Therefore, u star, that is the minimum of u and u prime, turns to be 8.5. Now you have to get back to the table and you can make the check that whether the null hypothesis, what was the null hypothesis? Just a quick reminder, null hypothesis for this particular problem was whether the median girth length or whether the location related to the variable girth in current variety and the location related to the hybrid variety, they are same, or hybrid variety location parameter is bigger. Okay, so quite common question in agriculture, that if you are trying to impose one hybrid variety, then obviously your concern will be whether this hybridization or hybrid variety will give you wider girth, the bushes with wider girth, right? So you just get back to the example question and you can just figure out the rest. Okay, now we will discuss another modification of Mann-Whitney U-test. Why I am saying it is a modification? Because in this proposal of the test statistics, we are trying to merge the rank, okay, the rank of the X observations as well as the rank of the Y observations, and that modification is done by Wilcoxon. So that's why it is called Wilcoxon-Mann-Whitney test statistic. Now you may ask me that why Wilcoxon-Mann-Whitney test statistic is necessary once we know Mann-Whitney U-test. Basically, you see that Mann-Whitney U-test requires all the time how many Y observations are superseding X observations. So basically, you have to count for each of the score of Y. Similarly, for each of the score of the X, you have to count always. So just to make the computational labor a little less, this modification we are going to propose. It is more straightforward towards the formula, right? So two-sample location problem can also be solved by two-sample Wilcoxon rank sum statistic, where we accept one-sided location alternative. Now we know that location parameter is defined as theta. Already we have defined in our earlier discussion. So H1, suppose theta greater than 0, that means Y is stochastically larger than X. Try to remember the picture I have shown you, picture of the distribution function X and Y. If the sum of the ranks of the X in the combined sample is too small, it's pretty clear. If Y is stochastically larger than X, most of the Y observations will be on the bigger side, right? Therefore, when you are ranking all the observations in the combined sample, what would you expect? You expect that the sum of the ranks of X's in combined sample will be smaller, right? The total sum. On the contrary, if you try to test the alternative hypothesis, X is stochastically larger than Y, just the opposite, then the sum of the ranks of the X in the combined sample will be too large. So keeping the view onto the rank sum of X as well as onto the rank sum of Y, Wilcoxon made a modification on Mann-Whitney test. So what is the Wilcoxon proposed test statistic? Here you will see YNX. So this is Wilcoxon. What is N? N is the total number of observation. You can see here M plus N. M is the first sample size and N is the second sample size. So YNX is Rx and YNY is RY. where Rx is the rank sum of X in the combined sample and Ry is the rank sum of Y in combined sample. Now, pretty interestingly, it can be shown that this Wn, which is based solely on the rank sum of X and the rank sum of Y. So, there are two versions of Yn. One is from rank sum of X observation and another is from rank sum of Y observation. It can be shown that this Wn is a linear transformation of Mann-Whitney U-test. Just a linear relationship they are holding for each other. So, what is that linear relationship? U is equal to Rx minus M into M plus 1 by 2 when X is stochastically larger than Y. So, you have to remember, when X is stochastically larger than Y, you have to consider Rx, that is the rank sum of X. Clear? And when Y is stochastically larger than X, then your test statistic will be Ry minus N into N plus 1 by 2. In practical scenario, we will use Wilcoxon-Mann-Whitney statistics as Wnx Rx minus M into M plus 1 by 2 or Wn y is Ry minus N into N plus 1 by 2. So, when alternative hypothesis is Y is stochastically larger than X, then you have to test by Wn and the test by U are equivalent. Okay. So, suppose you are dealing with Y is stochastically larger than X, then you can either go by the traditional Mann-Whitney U-test, means you have to count how many Y's are preceded by X observation, or it is easier. You see that calculating Wn is easier. You have to just make out the rank sum of Y and you figure out observations. So, the test by Wn and the test by U, they are equivalent. Equivalent means they are giving the same power, same critical point, everything. So, all the statistical properties of these two tests are same. The rejection rules remains the same as we did in Mann-Whitney test. So, that's a very important point not to be missed. The rejection rule means how do you reject? What will be the rejection rule? As you have done that U less than Mann-Whitney, I told you Mann-Whitney test statistic is a left tail test. Okay, smaller the smaller the value of U, stronger will be your rejection. Okay, so the same thing will be applicable in W. So let us solve example 1 from the previous lecture. The following data shows the age at the diagnosis of type 2 diabetes in young adults. Test if the age of diagnosis in males is higher of that of females. So these are the ages of the males under the sample 19, 22, 16, 29, 24. Age of females 20, 11, 17, 12. What was our concern? Our concern is H1, X is stochastically larger than Y. That means age of male is bigger than the age of Y in the population. So, as the rejection region is left sided, we can use Wn Y. Why? Wn Y is based on the rank sum of Y. If X is stochastically larger than Y, then what we'll expect? We will expect that rank sum of Y will be on the smaller side, right? Now, ordered combined sample. So, we have to combine two of the samples. Here you can see 11, 12, 16, 17. And by the side of the observations also I have mentioned the population or the sample figure, that it is coming from Y, it is coming from X, so on and so forth. Now, find out the ranks 1, 2, 3, 4, 5, 6, 7, 8, 9. We are saved because there is no tie case. See? So what is WNY? Rank sum of Y. So figure out the rank observation of Y. That is 1. Rank observation of Y is 2 here, and that is 4 here for 17, and that is 6 here. So it's just a calculation, 1 plus 2 plus 4 plus 6, and 4 into 4 plus 1. Why 4? Because look at the Y samples, 4 observations are there, right? So 4 into 5 by 2, and it turns to be, after the calculation, 3. Now see, this value is same as we did in our earlier lecture. The same you are having. That's what I'm saying, that Wilcoxon-Mann-Whitney statistic is exactly same as the Mann-Whitney U statistics. Now see the table. The same table, means the Mann-Whitney table will work here. Already you are familiar with Mann-Whitney table. So U tabular is 2 for m is equal to 5, n is equal to 4, and alpha is 5%, one-tailed test. Since U calculated greater than U tabular, what is U calculated here? You might be confused that this U calculated is nothing but this WNY, right? Because here we are considering Wilcoxon-Mann-Whitney statistics. So better to write like that, WNY greater than U tabular. We failed to reject the null hypothesis. So what was the null hypothesis? Null hypothesis was that the mean age of diagnosis of type 2 diabetes in male is the same of the mean age of diagnosis in case of females. So that is our null hypothesis. So we accept the null hypothesis. Now let's solve these couple of questions. One is that hybrid problem. Already we have done it manually, and another is the diabetes problem. Just now we did it. Let's solve these couple of questions using R. Okay. So this problem, the first problem doesn't have any tie case, while look at the second problem. We have modified this observation 36.7 so that it will matches with another 36.7 happens in the second sample. So second problem is of handling out the tie case. Okay, let's open the R window. Okay, so this is the R window. Already you people are familiar with R window. The first problem, that is the diabetic problem in between male and female observation. There is always one way of answering, that is you can incorporate the observation manually. So see, male, I have written here male, and the observations in terms of a vector C 19, 22, 16, 24, 29, female C 20, 11, 17, 12. So these are the manual incorporation, and we will look at this problem once again in case this example is given in a data set, given in a Excel file, given in a CSV file. That we'll do later on. Okay, let's start by this one. Male is this, so let me run it out. Female. Now you will always have a clear idea about the distribution of the male age and the female age if you can draw the box plot, right? And in the box plot you will see that how the median differs. So can you see the box plot on the right hand side? So 1 means the sample 1, means the population 1, population of the male's age, and 2 means the population of female's age, right? Now you will see that the median, that dark line means the median of the distribution. So median, of course, sample median, because what we have in our hand only the samples are there. So the sample median is that dark line, that black line. So quite sample median for first sample is quite higher than the sample median of the second sample, right? So back of your mind, one thing is clear, that might be their medians are not same, might be. Now just have a clear cut implication of Wilcox dot test. So Wilcox dot test, male is and female. So male is your first observation, female is your second observation or second sample observation, and the alternative you want to show that male age is bigger than female age. Okay, so alternative is taken as greater. So you will see that W turns to be 17 and p-value is 0.0556, and alternative hypothesis true location shift is greater than 0. So looking at the p-value is slightly bigger than alpha. If you fix alpha as 0.05, then with this p-value, what you can say that the null hypothesis is accepted, right? Now, I would like to show you another alternative way when, as I was saying, that when your data set is given in terms of a CSV file. Now, how that CSV file looks like? Suppose I have stored the CSV or stored the data into a CSV file like that. Okay, most of the time you have to work with the real life data. So suppose your real life is like that, data is like that, gender and age, right? Now you can always call the data by the option read.csv, and this is, as you know, D NPTEL class PPT. So all this blah blah is just the address of your CSV file. Header is equal to true, and you know what does it mean. Header is equal to true means one cannot ignore that gender and age. These are the headers of that two columns. Therefore, so let me run this data 1, and data 1, how does it look like? R will read that data 1 like this, gender, age, and you can see all the males are there and all the females are there. Now, what I am trying to show you, that if you have this type of CSV formatted data, then directly you can use formula interface. Formula interface is a super feature in R. Without manually incorporating the observations like we did here 1922, you can directly write data 2, that is a data frame. I'm making the data frame. So data 2 is made on that data frame, male and female, 5, 4, age and this, and directly what you can do, yes, now you see the data is equal to data 2. That means I am referring back that data 1 and data is equal to data 2. In fact, directly you can write here data 1 as well, no problem. Why data 1? Data 1 was the initial name of that data which I have stored in CSV file. Clear? Now we are making another data frame. Without making that data 2, you can directly go for that. The same thing you will have. W is equal to 3 and p-value. Look at the p-value. It's very interesting. Earlier, when you have incorporated your observations manually, 1920 like that, what did you get? You have obtained, let me get back, W is equal to 17 and p-value is exactly same, 0.055. But here, when you are using formula interface, age is formulated over gendered. This notation is meant for the formulated. So when you are doing that, you will find out W means the Wilcoxon test statistics value is 3 with the p value 0.005. Now one question might trigger that there we have written greater alternative and here we have chosen alternative as less. Then is there the difference between 3? No, that is not the difference. When you are using the formula interface, actually the structure, the R syntax computes U statistic. Means remember when I have first defined U Mann-Whitney U statistic, what I have done, if you want to show X is stochastically larger than Y, then the test statistic calculation was just the opposite. You have to see how many Y's are bigger than X. If your X greater than Y, the test statistic was just the opposite. How many Y's are bigger than X? Remember? So that's what is done by the formula interface. But when you are directly incorporating the observations, that is not maintained. It is taking straightforwardly X greater than Y. But when you are using formula interface, age is formulated over the gender, then that is calculated the left side rejection region. So everything I have put on as a comment, whatever I am saying, put on as a comment here. So don't get confused by having two W. One is W is equal to 17 and another is W is equal to 3. And moreover, you are already aware that what will be the total U plus U prime. Earlier I taught you U plus U prime is M into N. What is M? M is the number of observation in male. So that is 5 and N is 4. So M into N is 5 into 4, 20. So W and W prime or U and U prime, they are just conjugate to each other. So if the total rank sum or total pairing is 20, then 3 plus 17 must match the 20, and that's exactly what happens here. We are completely concerned about the p-value because that will guide us towards the rejection or acceptance of the null hypothesis. So your p-value is 0.055, which is bigger than 0.05, slightly bigger than 0.05. So we fail to reject the null hypothesis, and that is exactly we received while doing the same problem manually. Clear? Okay. Now we will go to the second problem. Second problem is a little easier because it's just you can go for, it is a two-sided test. So for two-sided test, you don't need to bother about whether you will write greater, alternative is equal to greater, or alternative is equal to less. Two-sided is much safer, in fact. So the second problem was the girth of current variety bushes and hybrid variety bushes. So X is 35.15, 27.6, so on and so forth. You people are aware how to incorporate the value, and Y is this. Now Wilcox dot test, then it is two-sided, but remember 36.7 repeats twice, so there is a tie. Then what you will have? You will have one warning message. When I am writing correct is equal to true, that means continuity correction is true. You have to make the continuity correction because of the rank, because of the tie, sorry. So you will have, even though you are having one warning message. Why? that is the exact distribution of the null distribution of the test statistic is not possible. So what you need to incorporate just to avoid, just to wipe out this warning message, you have to write exact is equal to false. That is okay, we are not in need of the exact distribution of the null hypothetical test statistic, okay. So there will be some modification. So let me incorporate exact is equal to false and run this. See, that warning message is not here. And look at W. W is 21.5. 0.5 comes because of that tie breaking, because of that 0.5 assignment of score. Remember, we did it manually also. And look at the p-value. P-value is 0.2722, which is way bigger as compared with the alpha. If you have fixed your alpha at 0.05, then it is quite bigger. Then we fail to reject the null hypothesis. That means the Garth of the current variety as well as the Garth of the hybrid variety, they are the same. Okay. So that's all about the R handling for these type of problems. Okay. So let's get back to our PPT formation. Now, in terms of tie case, as I have already explained to you, that you have to make use of that 0.5. Otherwise, your manual calculation will not match with the R calculation, right? That is number 1 point we have learned in this section, in this discussion. And number 2 point, how to read the R output when you are using formula interface and when you are manually incorporating the data. Please be very cautious about that, because most of the time we got confused that okay, one data, one problem, but we are having two sets of solution. Very clear that your formula interface uses the basic rejection technology which we have already discussed in the context of U statistic. Okay, so the left tail. So therefore, they are trying to figure out the lower side of the rejection. If x is stochastically larger than y, then formula interface uses how many y's are larger than x, and on the basis of that uy, they will give you the rejection. Clear? So that's all for this. Thank you.